Teresa, if you want, I think we can start.
Okay.
Good morning, everyone, and welcome to this week WST Time Domain Working Group Seminar Series. It's a great pleasure for me to introduce today's speaker, Teresa Sicignano. Teresa is a second-year PhD student at Scuola Superiore Meridionale of Naples and INAF Astronomical Observatory of Capodimonte. She is currently at TISO thanks to a prestigious granted studentship. Her PhD project focuses on the use of different distance calibrators in the extragalactic distance scale in the context of the Hubble constant debate. She is now working with the new spectroscopic and photometric data for a sample of galactic Type II Cepheids to derive a new period luminosity metallicity relation. Thank you, Teresa, for accepting our invitation. The floor is yours.
Thank you. Thank you, Julia, and also to Fateme for inviting me to this nice series of talk for the time domain group of WST. Julia already presented me, but I want to say that I'm a second year, the last week of my second year PhD. I will be soon third year PhD student from Naples, Scuola Superiore Meridionale and INAF Astronomical Observatory of Capodimonte, and I'm working at TISO since last year, thanks to a studentship during my PhD. Today I want to talk about Type II Cepheids and anomalous Cepheids as an alternative route to the Hubble constant. I think that almost all the audience know the motivation. This was firstly the motivation of my master thesis, and then we decided to continue to work on this topic, the Hubble tension, that is the phi sigma disagreement between measurement of each node coming from the late universe and measurement coming from the early universe. In particular, we are interested in the late universe measurement thanks to the extragalactic distance scale. Today, the most precise and accurate tree run to each node is thanks to the Schuss group, and as we can see here, this is based on classical Cepheids, starting from the period luminosity relation that can be calibrated through geometric indicators. Then we can reach the supernova 1A, galaxies hosting both supernova 1A and classical Cepheids. And thanks to this, we are able to measure each node through galaxies hosting supernova 1A in the Hubble flow. But I want to stress out that not only classical Cepheids can be used as distance indicators, where there are different pulsators that populate the instability strip and consequently follow a period luminosity relation. In particular, here we can see the pulsators of the LMC, and we are focused on Type II Cepheids that in this plot you can see my mouse, no, but now you can see my laser, I guess. Okay, we are focused on Type II Cepheids that are these BL Hercules and W Virginis. We will discover the difference, and on anomalous Cepheids, first over, fundamental and first overtone. Type II Cepheids, compared to classical Cepheids, they are all distance indicators. This means that can be found in all different type of galaxies. And whereas they are divided according to their period in BL Hercules and W Virginis. Indeed, BL Hercules pulsate among 1 and 5 days, and W Virginis among 4 and 20 days. And we are mostly concentrated on these two subclasses. And we can find them here in the instability strip. Indeed, anomalous Cepheids, they are intermediate mass and intermediate age pulsators that can pulsate both in fundamental and in first overtone mode, since they are giants with partially helium degenerate core. And they can pulsate around 1 day. And I want also to stress out that both anomalous Cepheids and Type II Cepheids, they are more luminous than RR Lyre, another quite important class of pulsators, but still less luminous than classical Cepheids. My work start analyzing data collected in the context of the Vista Magellanic Clouds survey, that is VMC, that is a NISO public survey observing Magellanic Clouds in the near infrared bands. Thanks to time series photometry, like you can see here, we derived the intensity average magnitude for Type II Cepheids in my first work. And here you can see the period luminosity relation only observed. And you can easily see how BL Hercules and W Virginis follow a very defined relation, especially in the near infrared band. Then we fitted this relation, both period luminosity and period basenite, whereas basenite is a magnitude-free, is a reddening-free magnitude for definition for these pulsators. And here, indeed, you can see the fitted relation with both BL Hercules and W Virginis. Thanks to the relation calibrated.
Just a moment, Teresa, that we have a question by Richard.
Sorry, because I'm not seeing the more over your screen.
Hi, Teresa. If it's okay to ask a question in between, otherwise I can keep it for later. I was wondering on the previous slide, do you have an idea where the scatter comes from in the points that you end up rejecting by a sigma clipping?
Do you mean
the scatter is quite high, you know, we're talking more than a magnitude of the PL sequence.
Yeah, but this point scattered, this is, I mean, first of all, this is only the period luminosity relation, and this is not the one that we are using in the near infrared band. Indeed, when we apply correction for reddening, this scatter reduces, and also this is mostly related to I mean, it's only about the magnitude of the observation, and it's related to just some stars that probably are close to another stars, and there is some kind of pollution from the other stars.
Blending.
Yeah, blending. Blending. I forgot.
Okay, but these are reddening corrected magnitudes here, right, with the 0.
Yeah, these are reddening corrected, but these are period luminosity relation, whereas we use the period basenite relation.
Okay, thanks.
You're welcome. Indeed, we used, here you can see an example of period luminosity in K-band and period basenite in the Gaia bands. We used these to calculate the distance of galactic globular clusters hosting Type II Cepheids, and our results seems to suggest that the distance moduli of galactic globular clusters appears to be overestimated up to 3%. And this was our first work with the Type II Cepheids. Indeed, regarding anomalous Cepheids, we started from the same point from the observation in the Vista Magellanic Clouds survey. And here you can see some examples of the liqueurs in the large and small Magellanic Clouds. And you can see the observed relation in the J and K band. We fitted this relation, and indeed you can see here both the period luminosity relation and period basenite relation for fundamental and for first overtone pulsators, and we decided also to try to fundamentalize for the first time the first overtone pulsators, and we found a new term to fundamentalize them. And this is important since means that we can use the same relation, we can slightly double the number of pulsators and so have a better statistics. And also here in the idea you can see that there are some scatter due to blending here, some kind of scatters, but almost all the pulsators are within 1 sigma in the relation. And so we also fitted this relation, and we published the results. And we decide to, in this case, to use the parallaxis of the parallaxis of Gaia DR3 for galactic ASEP, and to measure the distance of LMC in order to, quantify, in order to also to check our result and to see how well Gaia parallaxis work to calibrate our relation. And as you can see here, to retrieve a distance that is according to geometric distance of LMC, thanks to anomalous Cepheids, we need to use an offset of around 0.022 milli-arc second. Indeed, we also decide to calculate the relative distance among LMC and SMC, and you can see here the results that suggest a relative distance of 0.4. This means that SMC should be more close to us, whereas the geometric distances suggest us that the distances among LMC and SMC is 0.5. We also calculate distance to Draco, whereas Draco is a dwarf spheroidal galaxy that hosts both anomalous Cepheids and RR Lyre, and our distance is in agreement with the previous measurement of the distances of Draco through RR Lyre pulsators, but still slightly smaller. And as also suggested by Bardagi in 2023 in their paper, this can also be the cause can be to a metallicity effect that we are neglecting at this step. Indeed, I want just to say that period luminosity relation, as I anticipated, can be used as a first step of the extragalactic distance scale, but also to calibrate other classes of distance indicators, like the tip of the red giant branch. And here we can see how a different calibration would impact the value of each node. Now I want to focus more on the one kind of systematic that is still under debate for classical Cepheids. Indeed, in the community, we know that the luminosity and the period of a pulsator can also be affected by the metallicity, because as we can see in this plot by Trentin, a different metallicity will a different metallicity is linked to a different luminosity of a pulsator, and this means that also the metallicity contribute to a spread in the period luminosity relation, and this is also predicted by theory. But whereas for different kind of pulsators like the Type II and anomalous Cepheids, also theory suggests that there will be a metallicity span, but regarding the observational point of view, there are a few and non well concluding works based on based on a few sample, and I want now to present, to show you this part of my PhD, because these are spectra of Type II Cepheids that we are working on to have a period luminosity, a metallicity relation and period baseite relation of Type II Cepheids in the Milky Way. Indeed, the last run of ISO P115 under the PI of PI Bardacci, we observed 35 Milky Way Type II Cepheids, and under my PI we have also the TNG REM photometry, that is this photometry goes from the optical to the near infrared, and I'm still working on this data. And here I want just to show you how is a spectra of the spectra of these Type II Cepheids. We are still work in progress to derive metallicity to have the proper relation. We have also US accepted proposal for the next run. Moreover, we will have, yesterday there was the first light of Formos, so I think that yes, we will have Formos spectra of the same Type II and anomalous Cepheids in the Magellanic Clouds. And thanks to also supplementary targets call, we will also have metallicity, and a spectra of Type II Cepheids in the Milky Way. So we will be able to derive both period luminosity relation, metallicity relation in the LMC and in the Magellanic Clouds and in the Milky Way. And at this point, I think this is nice to see that this is like my PhD project. And at the end, thanks also to Gaia DR4 parallaxis, we want to compare the different distance scale, especially in the local universe, based on different pulsators to search for some remaining sort of systematics. But in the next, in the future, not the near future, but the more far away future, we will have also Gaia DR4 and also LSST data. We still have LSST data, but since we want to use them to classify and discover new variable stars, we need at least some years of observation to obtain a valuable period for our variable stars. And we will also have some observation in the high band that will allow us to observe, will allow us to have a period luminosity relation, and we will have, thanks to other different facilities that are coming, we can have also the near infrared bands.